Welcome to Week 8, Lecture 1 of EBME401. In the past 3 weeks, we've mostly talked about continuous time signals, but we're going to switch gears this week, and we're going to start talking about sampled signals, or digital signals. We'll also take a look at how the sampling affects our frequency domain in order to understand the concepts of aliasing. So again, so far, we've mostly been looking at continuous functions of time as our signals, and we've been denoting these as f of t. However, usually when we run an experiment, we won't have continuous functions of time, but rather discrete sampled points. So we're denoting our sampled signals now as f of n, where we put n in these square brackets to indicate that these are discrete time points, or f of n times delta t, where this delta t here is our sampling interval, and n is just an integer describing which sampled point we're talking about. So the first thing that we're going to look at is how we can convert continuous time signals to discrete signals using a process known as sampling. And understanding the process of sampling mathematically will help us better understand how sampling will affect the signal both in the time domain and also in the frequency domain. All right, so let's take a look at a specific example. All right, so first I'm going to draw a signal f of t. This is my signal in the time domain, and we see that I've drawn it as a continuous time signal. And I'm going to want to sample the signal. So we're going to represent mathematically the process of sampling as a multiplication of this f of t times a train of delta functions. And the spacing of the delta functions will be equivalent to the spacing of our sampling. So we're going to have some delta functions here, which are equidistantly spaced. And this is an infinitely long train. It goes on and on forever. And we see that we have a sampled point at 0, one at ts, one at 2 times ts, and so on and so forth. And we also will label the left-hand side. Okay, so this is our sampling function. And again, if we want to describe the process of sampling, we're going to multiply our continuous time signal by this train of delta functions. So here we'll just perform a multiplication between these two in order to get our sampled signal. So I'm first just going to draw the umbrella. So I'm first just drawing the envelope of my continuous time signal, and then I'm going to draw the results of the multiplication with these delta functions. So the sampled signal we get are just these modulated delta functions at 0, ts, 2 times ts. And again, this is still an infinitely long signal here. All right, so again, we see how we can represent the process of sampling mathematically. We're just multiplying our continuous time signal by a train of delta functions. This is going to give us our discrete signal here, f of n. So in other words, we're representing our sampling mathematically, again, as the multiplication of our continuous time signal and this train of delta functions. And here, this ts just denotes the spacing between our delta functions. All right, so we can write this this way here, again using this notation for a train of delta functions, or we can write this explicitly as a sum, where here this is again a way of denoting this train of delta functions that we're using as our sampling function. All right, so now we know how sampling is going to change our signal in the time domain. That's pretty obvious. However, we know that whenever we do something in the time domain, we will necessarily affect the frequency domain, right? This is kind of the theme of the past couple of weeks, that our frequency information is going to be affected whenever we change the time domain. Okay, so let's take a look at sampling in both the time domain and the frequency domain to understand how the sampling will affect both. So I'm going to draw my continuous time signal one more time. So let's say I have some infinite signal here. It looks something like this. This is going to be my f of t. And then I'll draw my sampling points here. So this is my train of delta functions, which again goes on forever and ever. And the interval between these points is TS. And again, mathematically, the process of sampling is just multiplying my continuous time signal, my train of delta functions, and the result is my sampled signal. So again, here's the envelope, and my signal is just sampled at these locations here. We'll call this my f of n, which has now been sampled. Okay, so what I'm going to do is look at each of these signals now also in the frequency domain. So if I move from top to bottom, I'm performing a Fourier transform. I'll do the same thing here and the same thing over here. So let's first start with the Fourier transform of my f of t, my time domain signal. Let's just assume that it looks something like this. It's just a very generic shape here. This is my capital F of omega. And again, the axis here is omega because I'm now in the frequency domain. So if I take the Fourier transform of my train of delta functions, the result is going to be another train of delta functions where my spacing is 1 over my sampling interval. Okay, so here I have a new train of delta functions where the spacing fs is equal to 1 over ts. And I also have to remember that if I'm performing a multiplication in the time domain, this is going to be equivalent to performing a convolution in the frequency domain. This is because of the multiplication and convolution properties of the Fourier transform. So here I'm going to be convolving my signals. And the result is going to be replicas of my frequency spectrum, capital F of omega, which appear everywhere that I have a delta function in my sampling function. All right, so I'll have exactly the same as capital F of omega centered around 0, but wherever I have a delta function at fs minus fs, I'm going to also have exactly a replica of the spectrum. And this is again due to the convolution between my capital F of omega and this train of delta functions with an interval of capital Fs. All right, so this is a very interesting result. I've taken a signal in the time domain and I've sampled it, so multiplied it by a delta function, or a set of delta functions. But in the frequency domain, instead of having a sampled frequency signal, I now have these replicas in the frequency domain. And these replicas are going to appear at 1 over Ts in my new frequency spectrum. Okay, so we've seen that I have the sampling interval, capital Ts, which I've written in seconds, and I can write my sampling frequency, so this is where all of my replicas are going to be centered in the frequency domain, as 1 over Ts. All right, so I've done a little notation change here, which might be a little confusing, so I want to go over it very carefully. Okay, so my sampling interval, Ts, is in seconds. All right, so my Ts here is also going to be in seconds. And my new sampling frequency is going to have then units of 1 over second, which is equivalent to hertz. All right. So far, our spectra have been functions of omega, which have units of radians per second. And so we're going to move to a slightly different set of units now when we look at our frequency spectra. And this will help us better understand where exactly our replicas lie with units that are a little bit more intuitive. All right, so we're going to convert these radians per second into units of hertz. And we'll do that by dividing by 2 pi, essentially. All right, so again, if I had a spectra with units of radians per second, and I divide that by 2 pi, and I'm going to end up with a spectrum that has a frequency of hertz. All right, so in other words, omega equals 2 pi f. And so we're going to write f for hertz, sometimes as a little f, and sometimes you'll see it denoted as this curly f here. This can also denote units of hertz. All right, so for the next couple of slides, I'm going to keep both our units of radians per second and also hertz, just so that we can get used to switching back and forth between those two. All right, so let's take another look at the replicas that we see in the frequency domain. So I'm going to again draw a discrete time signal. First I'll draw the envelope of my continuous time signal, and then we'll draw my signal, which has been sampled with a sampling interval of capital TS. All right, so there's my discrete time signal. We've already seen that if I perform a Fourier transform on this discrete time signal, then I'll see replicas in my frequency domain that are centered around Fs, where Fs equals 1 over Ts. All right, so here is the spectrum for the continuous time signal. And then here, centered at Fs, I'll see a replica. And there'll be another replica at 2 times Fs and 3 times Fs, so on and so forth. And there'll also be replicas here. Which look something like this. Okay, and again, there'll be more replicas in the negative direction. All right, so just to make this picture a little clearer, I'm also going to draw this line here at Fs over 2, and this line here at minus Fs over 2. And I'm also going to draw the bandwidth here of my signal here in the frequency domain. So the signal has a bandwidth of b. It extends out to b in this direction, and here to minus b in this direction. Okay, so in this case, we see that b here is smaller than Fs over 2. And so we can generalize this and say that as long as Fs is greater than 2 times b, these replicas that we see in the frequency domain are going to be distinct from one another. There won't be any overlaps in these replicas. However, we see that that might not always be the case, right? What would happen if Fs were less than or equal to 2b, right? And that is the case when Ts is greater than or equal to 1 over 2b, right? We simply invert both of these, and we know that this equals Ts. And so we see that the sampling interval, if we choose it to be too large, may lead to a situation where we no longer have distinct replicas in the frequency domain. Let's take a look at a case like that. So again, I'm going to draw the envelope of my continuous time signal, which is sampled at these discrete points. And we'll call this Ts prime, because it's a slightly different sampling frequency than what we had before. And we know that Ts prime will be equal to 1 over Fs prime, our sampling frequency. Alright, so here's my spectrum of the continuous time signal, which is now going to be replicated. So we'll call this line here Fs prime. And if I draw this correctly, we see that in this case, my bandwidth here is exactly equal to fs over 2. So in other words, fs is exactly equal to 2 times b. So in this case, I've increased my sampling interval and reduced my sampling frequency here so that my replicas are closer together. And in this case, they don't overlap, but they're just touching each other, these replicas in the frequency domain. So here I still have distinct replicas of my spectrum in the frequency domain, but just barely. And we could imagine getting to a point where I no longer have these distinct replicas in the frequency domain. So let's draw out that example. So again, here's my continuous time signal envelope. And I now have a very long sampling interval. Something like this, perhaps. And I'll call the sampling interval now TS double prime. And so I have TS double prime is equal to 1 over Fs double prime, my sampling frequency. Alright, so I have again my spectrum here. And let's draw my Fs double prime right here. And my minus Fs double prime. And we now see that these replicas are going to start to overlap. And in fact, if I draw the replica out here at Fs double prime times 2, we'll see that these will overlap, and so on and so forth. Alright, so in this case, when I have these overlapping replicas, I won't actually see the separate overlapping replicas. I'm just going to see the sum of all of them together. So what I'll see is something that looks like this as my overall spectrum. Is what my spectrum looks like for f of n with Ts double prime as my sampling frequency. Excuse me. So this is what the spectrum looks like for Fn with the sampling interval of Ts double prime. All right, and again, we see that the trouble here is that Fs is less than 2b. So my replicas again are starting to overlap, and I can't see the differences in these signals. Alright, so we've just seen what happens in the case where Fs is less than 2 times b. Alright, this is the case where the replicas in the frequency domain are no longer distinct. They're overlapping with each other. And again, because I have this connection between my sampling interval, Ts, and 1 over my sampling frequency, Fs, we'll see that this situation can happen if my sampling interval is selected to be too large for the bandwidth of my signal in the frequency domain, right? So when these frequency components start to overlap in the frequency domain, this effect is called aliasing. And what this means is that different frequency components in the signal can no longer be separated from one another. There's actually frequencies that should be represented as distinct frequencies, but they look exactly the same. The consequence this has on our actual signal in the time domain is that our sampled signal, f of n, is no longer a good representation of our continuous time signal. We're losing some of the frequency content that's contained in our continuous time signal, and it's gone in our sampled signal. And so in other words, the continuous signal, f of t, can no longer be reconstructed just from the points that I've sampled, f of n, again, if this sampling interval is chosen to be too large. So we saw a couple slides ago a sampling frequency for which the replicas do not overlap. There's no space between them, but they're not actually overlapping. And this sampling frequency is called the Nyquist sampling frequency. So the Nyquist sampling frequency, Fs, is exactly equal to 2b. The Nyquist sampling interval is defined as TS equals 1 over 2b, because we know that TS is equal to 1 over Fs. And this sampling interval is the largest sampling interval that we can use while avoiding aliasing in the frequency domain. If we use a longer sampling interval, then our frequency replicas are going to be closer together and they will start to overlap, so there will be aliasing. Of course, if we use a shorter sampling interval, our replicas will be further away from one another, and there still won't be aliasing. But we often want to find the longest sampling interval that we can use while still capturing the frequency content of our continuous time signal. All right, so let's take a look at exactly what the sampling interval is again. So this time we're going to start in the frequency domain here. All right, so we imagine we have the spectrum of our continuous time signal, and the spectrum has a bandwidth of b, so it extends to b in the positive direction and minus b in the negative direction. And here we're going to let, again, our sampling frequency, Fs, be exactly 2 times b. And we'll see in this case, the replicas will end up just exactly touching, but not overlapping. All right, and this is minus Fs. And of course, there'll be replicas out into infinity, but we're just looking at these two here. All right, so again, because these intervals don't overlap, we can exactly recover the continuous time signal f of t if we can filter out these replicas. So we would want to apply a filter with the following frequency response. And if we could apply this filter here, we would exactly be able to eliminate all of the replicas while retaining exactly the spectrum right at the center. And this filter would enable us to take our discrete time signal and recover the continuous time signal. And this will be covered in more detail in the text. All right, so we know again that the replicas in the frequency domain are going to be controlled by the sampling interval that we use in the time domain. So this is our time domain. Here's the envelope of our continuous time signal. And this signal is sampled at discrete intervals. Where here, the distance Ts is exactly 1 over 2b. So in order to determine exactly the appropriate sampling interval, we need to have a knowledge of the bandwidth. And of course, the bandwidth here is defined in the frequency domain. And so we have to know what kind of frequencies we expect in our signal so that we know how we can appropriately sample it. So let's take a look at an example. So this is an example of a sinc squared function in the time domain. All right, so here our function f of t is sinc squared of 5 pi t. So this guy is actually going to extend out to infinity, but we're really just focusing on the center portion. Okay, so here our f of t is our continuous time signal. So we haven't done any sampling yet. And you can see that our f of t goes through its first zero at minus 0.2 and 0.2 in the time domain. We can perform a Fourier transform on our f of t in order to calculate the spectrum for the continuous time signal. This is capital F of omega. Right, so if we just use our Fourier transform tables and all of these properties, we'll see that the spectrum of the continuous time signal is 1/5 times the triangle function with an argument of omega over 20 times pi. And so this triangle function is going to look something like this. Here you can see it, I'm outlining it in black. All right, so and I've drawn the frequency axis in both units. So we have omega, which has units of radians per second. And so here the bandwidth in radians per second is 10 pi. But I've also drawn the frequency axis here in hertz. And so here the bandwidth of our signal in hertz is going to be 5 hertz. Okay, so B for the signal will be equal to 5 hertz or 5 inverse seconds. right? And again, this bandwidth is important when determining our Nyquist sampling interval. So this is going to tell us how we need to sample our signal in order to represent it appropriately. Okay, so let's start by sampling our signal at exactly the Nyquist sampling interval. All right, so again, our bandwidth is 5 Hertz, and so the Nyquist sampling rate, Fs, is going to be equal to 2b, and so Fs will be equal to 10 Hertz. We then can convert this sampling rate into a sampling interval. So the sampling interval that corresponds to the sampling rate, Ts, will be 0.1 seconds, a tenth of a second. All right, so again, if we want to appropriately sample our time domain signal so that we don't have any replicas overlapping in the frequency domain, we need to use a sampling interval of a tenth of a second. So this means we've sampled our signal at time t equals 0, t equals 0.1 seconds, 0.2 seconds, 0.3 seconds, 0.4 seconds, and we'll also do here this negative time portion. All right, and so on and so forth. So we're going to keep sampling this guy forever. Okay, so we know now that given a sampling interval of 0.1 seconds, we're going to have replicas in our frequency domain every 10 Hertz. All right, so let's draw a 10 Hertz line here. All right, this is exactly 10 Hertz. And we see that we have exactly a replica of our original spectrum centered at 10 Hertz. We have another that's centered at exactly 20 Hertz. And these would go on forever. And the same thing on this side. We have a replica centered on 10 Hertz and a replica centered at 20 Hertz. And because our sampling frequency is exactly equal to 2 times the bandwidth, we don't have any overlaps. And as we've seen before, this means that if we can apply an ideal filter at exactly the bandwidth of our spectrum, we could filter out all of the rest of those replicas, and that would enable us to reconstruct exactly this continuous time signal here, which I'm drawing in green. Right? So if we use the sampling interval and the sampling frequency, then we see that the sampled points here that we've drawn in red are a good representation of the continuous time signal, which we're drawing in green. Okay, so again, because our replicas don't overlap, we have a good representation of our time domain signal. Well, what happens if we sample our signal more frequently? So we use a shorter sampling interval. Before we said the Nyquist sampling interval was a tenth of a second. Well, what if we change our sampling interval to a 20th of a second, or 0.05 seconds? All right, so we now have sampled points at 0 seconds, 0.05, 0.1, 0.15, 0.2, also minus 0.15, minus 0.1, minus 0.15, minus 2, again, so on and so forth. I'm not going to draw the rest of them out. Okay, so our TS is equal to 0.05 seconds, and 1 over TS, which is our sampling frequency, is going to be equal to 20 Hertz. So this means our replicas will now be spaced at 20 Hertz intervals. If we take a look at our replicas, we see that that's exactly how we've drawn them here. Our first replica here appears here at exactly 20 Hertz. We have a replica at minus 20 Hertz, and we'd have replicas at 40 Hertz and minus 40 Hertz. We just haven't drawn them here. So we saw that when we used the Nyquist sampling frequency and the Nyquist sampling interval, we needed a perfect ideal filter in order to filter out our replicas to reconstruct our continuous time signal. Well, in this case now, we see that our replicas are further apart, and so we may be able to use a practical filter, so something that would have a frequency response looking something like this. And that would still be adequate to enable us to recover our continuous time signal, which you can see over here. All right, so we saw a couple of lectures ago that building a perfect filter is impossible. It's actually easier to build this practical filter, which has some transition band, a slightly longer roll-off than an ideal filter. And so by separating these replicas in the frequency domain using a shorter sampling interval, we have a better chance of actually being able to recover the continuous time signal. And so even though the Nyquist sampling interval and Nyquist sampling frequency allow us, in theory, to reconstruct our continuous time signal, it might make more sense to use a slightly shorter sampling interval so that we can be sure that we don't have replicas overlapping in the frequency domain, which enables us to recover our continuous time signal. What if we do exactly the opposite? So we found out that our Nyquist sampling interval was 1/10 of a second. But what if we increase the sampling interval from 1/10 of a second to 1/5 of a second, or 2/10 of a second? So this is going to be our new TS. All right, so let's see, we now have a sampled point here at t = 0, and a sampled point here at 0.2 seconds, and 0.4 seconds, minus 0.2 seconds, minus 0.4 seconds, and so on and so forth. All right, so what's happening now in our frequency domain? Well, our fs is now 5 Hertz. So let's find our fs here, exactly 5 Hertz, and we see that we have a replica centered exactly around 5 Hertz. I'm also going to draw this replica at minus 5 Hertz. In orange, I'm going to draw the replica here at 10 Hertz. And then here in orange, I'll also draw the replica at minus 10 Hertz. So here I've just drawn a couple of my replicas, but you can see on this schematic, I'll have replicas at all these intervals of 5 Hertz. So 5 Hertz, 10 Hertz, 15 Hertz, 20 Hertz, all the way up to infinity, right? And we see that we have a lot of overlap in these replicas. And as I said before, we don't actually see these overlapping portions in our frequency spectrum. We'll see the overall sum of all of these replicas. So the spectrum that we actually get from our sampled signal is going to look actually like a straight line. This is by adding up all of the contributions of all of these replicas in the frequency domain. All right, so instead now of seeing a spectrum which looks like a triangle or a set of replicated triangles, my frequency spectrum just looks like a constant. All right, that's strange. This is a consequence, though, of sampling really slowly in the time domain. So let's take a look back at this time domain and see actually what our sampled points look like. So we see we've sampled a point right at t = 0, which is equal to 1. But the way we've sampled our signal, it just so happens that every other sampled point is equal to 0. And so if we just had our sampled points, just the blue lines and dots on the left-hand side, all we would see would be the point at t = 0. In fact, that means our sampled signal is really indistinguishable from a delta function. And we know that the Fourier transform of a delta function is just going to be a constant. So sampling at this interval actually will give us this funny constant spectrum that we see in the frequency domain. And this just a result of picking a sampling interval that was much too long for our sinc squared. All right, so this is kind of an extreme case of the consequences of aliasing, that if we pick a sampling interval that exactly misrepresents our signal, we can end up not being able to tell what the form of our signal was at all. We see no spectral information in this constant in the frequency domain. And our time domain signal, which used to be a sinc squared function, we can't tell that from a delta function. All right, so we see how moving to a long sampling interval can cause us to lose all of the information in our time domain and our frequency domain, right? We can clearly no longer replicate the sinc squared continuous time signal from the frequency domain. All right, so this previous example, again, was a very extreme example of aliasing. But in general, aliasing will eliminate or, at best, just obscure the information in our signal. So, in the previous slide, we saw that the sinc squared function couldn't be distinguished from a delta function. This is pretty extreme. But often the effects are more subtle, but they still can be present. So let's take a look at an example, a very simple schematic, to understand how this can be. All right, so let's imagine we have a signal where the signal itself is the phase of a spinning arrow. So we have an arrow at the top of the screen, and this arrow is spinning. Okay, so the spinning arrow represents our continuous time signal. We can see the spinning at all times of t. But imagine instead of being able to see the continuous time spinning arrow, imagine that we just take snapshots of the location of this arrow at certain times. This will correspond to our sampling interval, Ts. So let's let our sampling interval be equal to 0.25 Ts. So at t equals 0, our arrow is pointing straight up. And after one interval, we sample our signal again, and we see that our arrow is pointing exactly to the right. We let another Ts interval go by, so at t equals 0.5, our arrow is pointing down. At t equals 0.75, our arrow is pointing to the left. And at t equals 1, our arrow is pointing up again. So this here is all of the information that I have. And imagine I ask you, using this information, not knowing about the actual continuous time spinning arrow, imagine I ask you what the rotational frequency of this arrow is. All right, so one option would be that our arrow is spinning at 1 cycle per second. So it's spinning clockwise, and every second it performs exactly 1 rotation. All right, this is actually what's happening in our continuous time signal, and we know that because we've seen the arrow spinning. However, there's a couple of other answers that we could give with this particular sampling interval. So one thing that we could say is that our arrow is spinning at -3 cycles a second, or 3 cycles a second in a counterclockwise direction, rotation to the left. Right? This would give us exactly the same sampled points that we have that I've circled in green. Right? There's no difference between the sampled points between this case and this case. Right? Another option would be that our arrow is spinning in a clockwise direction, but much faster than it actually is. So we could say, for instance, that our arrow is spinning at a rate of 5 cycles per second, or even 9 cycles per second. Right? All of these 3 cases are indistinguishable given this information that we have right here. We absolutely can't tell the difference. And so at this sampling interval, none of these frequencies can be distinguished. This is exactly what it means for different frequencies to be aliased. We can't tell the difference between any of these 3 frequencies at this sampling interval. So let's take a look at the problem of our rotating arrow now in the frequency domain. So first we'll write an equation for our continuous time domain rotating arrow. So f of t is going to be equal to cosine of 2 pi t. This corresponds to 1 rotation per second, which is what we saw that our arrow was actually doing. And we can transform this time domain signal into the frequency domain using the Fourier transform, and we see that capital F of omega is the sum of 2 delta functions. So this makes sense, of course, because the cosine in the time domain should correspond to 2 delta functions in the frequency domain. So this equation here is for units of radians per second, and this bottom equation is corresponding to units of hertz. Let's focus on the bottom equation because we usually deal with units of hertz for these sampling problems. Okay, so we see that our 2 delta functions here in our continuous time spectrum are located at 1 hertz and -1 hertz. This is exactly what we would expect. Okay, so we remember in our arrow rotating problem that we used a sampling interval of 0.25 seconds, which corresponded to a sampling frequency of 4 hertz. And so we're going to have replicas of our delta peaks, which are centered around 4 hertz. So we can add in here our minus fs and our fs located at 4 hertz, and also these additional peaks which correspond to replicas which are centered around minus fs and fs. So just for clarity, the orange lines are now our original continuous time spectrum, and the red arrows are the additional peaks which we have due to our sampling. Okay, so we see that in our original spectrum we had a bandwidth here. So in our original spectrum we had a bandwidth of 1 hertz. Okay, and so we know that if we want to properly represent our signal, we have to make sure that our sampling frequency, fs, is greater than or equal to 2 times our bandwidth. So here we have 4, which is greater than 2 times 1. And so we're able to properly represent our rotating arrow if we use a sampling interval of 0.25 seconds, right? So in other words, again, we can use a low pass filter just to keep the portions of the signal that are centered around 0. We could filter out all of the replicas in the frequency domain, which would allow us to reconstruct our continuously rotating arrow in the time domain, right? We could assume that we knew exactly what that was, only using those snapshots that we had taken every 2.05 seconds. Let's now look at the case where we had an arrow that was rotating counterclockwise at 3 rotations per second. So I've now changed my f of t to have a new rotational frequency. So this corresponds to -3 cycles per second. Okay, so I'm going to go through the same operation. I'll take my continuous time signal and transform that into the frequency domain. And so we see now my signal should be made up of 2 delta functions, which are centered at -3 Hertz and 3 Hertz. And that's exactly what I'm showing here. Right, so here's -3 Hertz and 3 Hertz. Okay, so my bandwidth now has changed. My bandwidth, B, is going to be equal to 3 Hertz. All right, so let's go back to how we performed our sampling. So we have the same sampling interval, 0.25 seconds, and the same sampling frequency, which is 4 Hertz. And so we know, again, because we've sampled, we're going to have replicas of these 2 delta functions, which are centered around -4 Hertz, 4 Hertz, 8 Hertz, so on and so forth. Right in where our -Fs is and our Fs. And we can start to draw the peaks that we would get now from aliasing. So we'll have a peak here. So we can start to draw now the peaks that we would get due to our sampling. So we have a peak that's centered at -1 Hertz and a peak that would be centered at -7 Hertz. And here we have a component at 1 Hertz and a component that's centered here around 7 Hertz. All right, so let's see what's happening here by looking at how our sampling frequency relates back to the bandwidth. So we know that our bandwidth is equal to 3 Hertz. So 2 times our bandwidth is going to be equal to 6 Hertz. And we also know that our Fs is equal to 4 Hertz. All right, and so in this case, our Fs is going to be less than 2 times our bandwidth. And in this case, this is where we expect to have aliasing. And we see that this is exactly the case, that we can't draw a low-pass filter around the peaks that we actually do have in our signal, these 2 green delta functions, without including these additional peaks due to aliasing. All right? And this explains why our arrow rotating at -3 cycles per second looks exactly like an arrow that's rotating at 1 cycle per second. Right? Because we have this aliasing, the peaks are going to be completely indistinguishable from one another. And what this means is that we can't distinguish these frequencies from one another. All right, this is the problem with aliasing, now explained in the frequency domain. But again, we can't tell whether our arrow is rotating at 1 cycle per second or -3 cycles per second, or we'd see the same thing for 5 cycles per second, and so on and so forth. And so I think that this example makes it a little bit easier to understand exactly why we can't distinguish these frequencies, now looking at the frequency domain. All right, so aliasing is painful. So we've seen that if we have frequencies in our signal that are higher than Fs/2, these frequencies will be completely lost. So we can't capture these very high frequencies with our sampling interval because they're happening too quickly for our long sampling interval to be able to capture. All right, so any frequency that's higher than Fs/2 will just be completely misrepresented if we use a sampling interval that's too long. We also see, though, that frequencies that are lower than Fs/2 are going to be corrupted, because the higher frequency signals that we lost are going to appear in this lower range. Essentially, we fold the higher frequencies back down to lower frequencies. And so what this means is that not only do we lose our high frequencies, but we also are affecting our low frequencies due to this aliasing. So we may see low frequencies in our signal that aren't present in the continuous time signal, but what these are actually high frequency signals which are aliasing down to these lower frequencies. But really the most painful thing is that we can't tell the difference between actual frequencies and these aliased frequencies, right? We saw in the example of the rotating arrow that we wouldn't be able to tell the difference between an arrow that's rotating at 1 cycle per second or 5 cycles per second. These two frequencies look exactly the same at the sampling interval that we've selected. And so if we have interesting information happening at 1 Hertz and interesting information happening at 5 Hertz, these will exactly fall on top of one another and we won't be able to tell the difference. All right, so this is why aliasing is really detrimental to signal collection. We have to be very careful when we select our sampling interval so that we don't end up with frequencies that look the same. Okay, so unfortunately, aliasing in real life will always occur. All real life actual collected signals that we're going to work with are finite. And so if they're finite in the time domain, we know that in the frequency domain, they're going to be infinitely large. They'll have an infinite bandwidth. So any finite signal in the time domain, may have a spectrum where the interesting information is happening at these lower frequencies, but we're going to have some frequency content out at the high frequencies, no matter what we do. And so even if we select a very short sampling interval, so our sampling frequency is way out here, and we replicate exactly our spectrum here again at minus Fs and Fs, right? We may not have a lot of aliasing, but we're still going to have always aliasing of these high frequency components back into our lower frequency components. And this is again because we have an infinite bandwidth frequency spectrum in any real life signal. And so even if most of our signal energy is appearing in a very small bandwidth here, which we'll call B, there will still always be alias signal appearing within this bandwidth. All right, so what can we do about this? Because we don't want to corrupt all of our low frequency information with aliasing from high frequencies that are coming from this real life signal, which ends up having an infinite bandwidth. All right, so there's a couple of things that we can do to avoid aliasing when we sample our signal. So the first thing that we can do is increase the sampling frequency. All right, so in other words, we can decrease our sampling interval. So by decreasing the sampling interval, we're collecting points faster, which allows us to capture more of this high frequency information. However, this won't completely solve the problem. One thing that we can do is include in hardware, before we perform our sampling, a low-pass filter. So what this low-pass filter is going to attempt to do is eliminate signals that are higher than Fs over 2. All right, we call this hardware filter an anti-aliasing filter. All right, so if we can attenuate all of our high-frequency signals, then once we sample them, they won't fold back into the lower frequency portions of our spectrum. And so we won't have the aliasing that we would have gotten without this filter. All right, so this anti-aliasing filter must be applied before we sample the data, right? Once we've sampled the data, then we already have our frequency information and our replicas, they're already set. And so there's no way to get rid of our aliasing once we've sampled it. All right, so this is really, really important. Our anti-aliasing filter must be applied before we sample our data. And once again, once our sampling occurs, we can't get rid of our aliasing using normal signal processing techniques. All right, so if we sample our signal at an interval that's too long, and so our frequencies are indistinguishable, we can't recover this higher frequency information after we've sampled it. All right, so we have to be very careful to pick a sampling interval that is proper with the knowledge of the highest frequency that is contained in our data. All right, so this has been a whirlwind looking at how we can sample our signal and how we choose an appropriate sampling interval based on the bandwidth that we have in our time domain signal. And so we're going to look at some of the implications of this in the text readings and then talk about digital filters in our next lecture. All right, thanks a lot.